Welcome back to Engineering Mechanics, and today we will talk about forces in 2D spaces. So let's take a look at what our real goals are for today. So first of all, we want to reiterate our trigonometric laws so that we know how to apply them to force systems in engineering mechanics. And then we want to talk about forces and force additions. For that, we really will use vectors, so that ultimately we can compare trigonometry to 2D vector description. And then at the very end, we will hopefully be able to use vector addition and vector decomposition to describe 2D force systems, and those are planar force systems. So let's get started and recall our trigonometric laws. Of course, we remember that every time we deal with any random triangle, we really need the trigonometric laws if we want to know more about the angles or the length relationship. If it's not a right angle triangle, then we want to use the cosine law and the sine law. And this has been provided to you in previous lectures that are available for you. So let me just rewrite quickly the cosine law. Remember that c square is equal to a square plus b square minus 2ab and gamma. And that was derived in a different lecture for you. However, I want to quickly focus on these entities in the context of engineering mechanics. So first of all, how do I memorize this formula very well? It's pretty much Pythagorean theorem minus the specific angle here. And this angle is not a random angle. You really need to know how this angle is defined to use it properly in engineering mechanics. And that angle is the one between the side A and B. So for example, if I call this here side A, B, and C, then I would have a gamma angle right down there because it's enclosed between A and B. And so that is independent of how the triangle is oriented in space, because it will always relate to the angle between A and B. And it doesn't matter really if you call it A and B, as you will see later in the examples. You just have to be able to apply it properly, and that's really why we're recalling these trigonometric laws here. Similarly, for the sine law, so the sine law states nothing else than that the sine of alpha relative to side A is equal to the sine of beta relative to side B, which is equal to sine of gamma, which is relative to side C. Some people write this upside down. It really doesn't matter. However, the same thing applies here. You need to know where A is relative to B and to alpha and to gamma and so on and so forth. So if I have another random triangle here, it is just that if I have side A, B, and C, then for example here I would have my alpha. And so if I want to use this formula, I have to obviously use the proper relationship. So A would be this side, alpha would be this angle, and then B would be this side, and then beta, which would probably be an unknown, would be the angle here. And my goal next now is to explain to you where we can use these in engineering mechanics. In fact, I think we already are ready for an example, because it is just a quick review of the trigonometric law. So let's put this to application. So here we have our very first real problem in engineering mechanics. And the first thing we always need to do when we look at problems is to really read and understand the problem statement, because we often ask you very specific techniques. And here in this case, we are asking for trigonometry. So you can, of course, use this problem or solve this problem in many other ways. For example, a lot of you probably would resort to vector decomposition, but please pay attention. This is definitely not allowed in this case, because we want to make sure that you are familiar with the technique that we need for this. So what are we supposed to do? We are supposed to determine the resultant force on the I hook and the angle that that resultant force has. So let's take a look at that problem here. we have two forces. They both pull away from the origin of the coordinate system. The first force pulls with 15 degrees, the second one with 10 degrees, and you see the amount that they are pulling here. It is always good to have a sketch first, and you may remember this from your basic physics class, that you can use your parallelogram to find the resultant in a force system. So let's do that. I first will move my F1 parallel along this line, and then I will move my F2 parallel along this line here. And now the diagonal within that trapezoid is really my resultant force. So let me put that in for you. So this would be the resultant force, or this would be the visualization of it. So F resultant is what I call that. And now we have to find that resultant force and its angle. Let me show you where the angle is. So the angle would be this distance here. And it's important that, let's call that theta, that is measured from the positive x-axis. So from the positive x-axis towards the positive y-axis, so that means counterclockwise positive. That means we're measuring in this direction. This may be very clear to you in this example, but sometimes we are in the second quadrant or the third quadrant or the fourth quadrant, but you always have to measure from the positive x to the positive y. So that would be counterclockwise positive. All right, but how do we do this now with our trigonometric laws? Remember the trigonometric laws, the cosine law, we just wrote it down. I do it once again. So c square is equal to a square plus b square minus 2ab cosine gamma. So now how do I apply this here? Well, I would argue that it is easiest to apply it in the fashion that I'm looking for the F resultant. So F resultant would probably be my C, and then I have A and B. And so all that's left to do for me is to find the angle gamma, which is that angle gamma. It's the one between A and B, remember, right? So it's the angle right here. So let me maybe first transcribe the equation, and let me say that F resultant is really equal to F1 squared plus F2 squared minus 2F1 F2, and then the cosine of an angle that I'm not aware of right now. And there lies the first challenge. So let's look at that angle first. So really I need this angle, and let me call that gamma. And gamma can be found. There are some traps here to fall into, but let's talk about them. So first of all, I know that it's a parallelogram, right? So I know that this entire figure here is a parallelogram, and therefore I know that all angles in the parallelogram, this angle plus this angle plus this angle plus this angle is 360. So I can state that 360 is equal to, and now I need to look closer again. So I have this angle, which is identical to this angle, so effectively 2 gamma, and then this angle here. Let me identify that as well. So let's say this angle here, that angle is really equal to 90 minus 10 minus 15. So I know that this angle is really equal to 65. And now, once again, I have this angle acting here and here. So all I have to do is say that 360 is equal to 2 times gamma plus 65, which is also 2 times, right? So in other words, I have 180 being equal to gamma plus 65, and therefore gamma is really equal to 180 minus 65, and that equals 115 degrees. And now I pretty much solved the problem. However, don't be fooled when you follow me on these examples. This is the starting point and the equation everybody gets right from the start. But the question is, are they able to find the angle? And now I showed you how to do that in this case. Of course, every geometric case can be different, and that's why you get the homework to practice that. So now we know 115 degrees, is gamma, and now I can start solving my equation. So let's go ahead and do that. So let's say that F resultant is really equal to 100 Newton squared plus 150 Newton squared minus 2 times 150 Newton times 100 Newton times the cosine of 115 degrees. And if I solve this, by the way, this of course is F resultant squared, but if I solve this for F resultant, I will find that I now have 212.6 Newton. And so this is a result, and that result I need to double underline as always, because that is specifically what was asked of me in the problem statement. And this 212.6 Newton is effectively the length of this arrow. And so we completed the first part, which is the resultant force, but now we need to find the angle of that resultant force. So how do we do that? So the resultant force is really that purple theta there that I marked for you, this angle here. And now I will find that by using the sine law to identify this angle inside and then add the 15 to it. And there's one trap that students often fall into. Students like to believe that this angle here is equal to this angle, or if I show it down here, this angle is equal to this angle. But this is not the case. That's only true, if you think about it, for very specific types of trapezoids, and of course for a square. So don't fall into that trap. This angle is different than this one usually. And so therefore I have to calculate this angle first. So let's go ahead and do that. So my formula is, as I stated before, A to sine alpha, just as B to sine beta, for example, or C to sine gamma. Now, how do I apply this? So let me name some things here. I have my gamma here, so I have this fulfilled. And again, keep in mind that gamma is opposite to C. So opposite to C is actually my F resultant. So I already have these two fulfilled. And now if I want to find this angle here, I would have to use the opposite, which is along this line. And that is really F2, right? So now I have to use F2 here. So if this is alpha, let's pretend that's we're going to call that alpha. And let me mark that up for you. So from here to here, that's alpha. So if I want to find that angle alpha, I just have to use my F2 as A. And therefore I have F2 relative to sine alpha is equal to F resultant to sine gamma. And now all I have to do is solve this effectively for sine alpha. So I bring that to the other side, bring these over. Let's do that real quick. So that sine alpha is equal to F2 over F resultant times sine gamma. And now all I have to do is populate that with numbers. And in fact, I can immediately state that alpha is equal to sine inverse of my F2 was 150 Newton. And my F resultant was 212.6 Newton. And then I multiply that by sine gamma, which was sine 115 degrees. And that gives me my alpha angle. And that alpha angle happens to be 39.8 degrees. However, be careful, because that's not the true answer here. We're not looking for that angle. We're actually looking for the angle theta, right? We're looking for this angle from here to here. So I now have to add 15 degrees to it. So let's do that in our last step. So my theta is really equal to 39.8 degrees plus 15 degrees, and that is equal to 54.8 degrees. And that, once again, is an answer to what was really asked of us. I only have to find and double underline the answer to what's really asked. And of course, I always add my answer arrow. And I have to do that for my first answer as well. Of course, here in the lecture, that's different than on engineering paper. But that concludes this problem, and so therefore I have my answers provided. Let me reiterate real quick that the downfall of this problem is not actually solving the solution, as many things in mechanics. It's not solving the numerical part. It's usually setting up the equation and finding the starting point. So when students in the exam usually get this wrong, they usually mess this one up. And that is something which, I can show you in this case, but again, you need to practice that for different geometric features or different geometric arrangements. So please try to study up on that and get ready for that, because this is effectively a good problem number 1 on an exam. But this concludes the trigonometry part, and now we can move on to vector analysis.